In 2012, a new particle was discovered by the Large Hadron Collider. Scientists believe that the Higgs boson has finally been found. But what's the big deal with the whole Higgs thing anyway? The Higgs field is thought to give mass to fundamental subatomic particles like the quarks and the leptons that make up ordinary matter. The Higgs bosons are the wiggles in the field. But how does this field give mass to particles? Suppose there's a large cocktail party at CERN filled with particle physics researchers. The crowd of scientists represents the Higgs field. If a lawyer entered the hall, nobody would want to talk to him and he could very easily cross the room and reach the bar. The lawyer wouldn't interact with the scientists in a quite similar manner that some particles don't interact with the Higgs field. The particles which do not interact with the field, like photons, are massless. Now suppose that Peter Higgs entered the same room searching for a drink. The scientists will immediately gather around him to discuss their efforts to measure the properties of his namesake boson. Because he interacts strongly with the crowd, Higgs will move slowly across the room. Continuing our analogy, Higgs has become a massive particle through the interactions with the field. So if that's the Higgs field, where does the Higgs boson fit into all of this? Let's assume that our scientists in the hall are uniformly spread across the room. Then someone pops in the door and reports a discovery at a rival laboratory. People near the door will hear the rumor, but the people far away won't. So they'll move closer to the door to ask. This will create a clump in the crowd. As the people have heard the rumor, they'll return to their initial positions to discuss its implications. But the people further away will then inquire what's going on. This will create a clump in the crowd that moves across the room. This clump is analogous to the Higgs boson. So we can say that mass comes from the interaction of the field. The Higgs boson is an excitation of the Higgs field. In the Large Hadron Collider, two protons are accelerated to very high energy, practically the speed of light. The protons are composed of three quarks kept together by a number of gluons. When the two colliding protons get very close and overlap, an energetic gluon is emitted from each of the protons. The two high-energy gluons merge in a very energetic gluon fusion. This fusion results in the production of a Higgs particle. This unstable particle, in an unusual event, then decays into two photons. So the Higgs boson is like a quantum ripple in the background energy field of the universe. Interacting with this field is how all fundamental particles get mass and thus matter exists. Deep study of the Standard Model continues. Precise measurements of particles and forces that make up the universe are being used to unravel how gravity fits in, or the relation between matter particles and force carriers, or understanding dark matter. There's a universe worth of mysteries left to explore.